Today we're going to talk about similarity in right triangles. Okay, so before we talk about similarities in right triangles, we need to review a little bit about proportion that looks like this. Who remembers? I have a proportion A over X equals to Y over B. What X and Y are called? Yes, sir?
Means.
That's correct. These are means. And of course, A and B are the extremes. You guys remember that?
Yes.
Okay, so there's a reason why we're talking about this, because some proportion are written this way. Kind of interesting. If you have A and B and X are positive numbers, and if you have a proportion that happens to be this way, A over X equals to X over B. In other words, the means are what? If they're the same, okay, we have a special name for these mean. Anybody know what they're called? No, it's called geometric mean. Okay, so I'll write that down. If this is a special type of a proportion, if you have a proportion that happens to have the same mean, those means are called geometric mean. Okay?
Wait, why doesn't it work if it's negative?
Oh, okay, because we're going to talk about something about right triangles and the length of these segments and so forth. So we're going to talk about just positive numbers. Is that okay? Yes, sir.
We start copying from if.
Right, so start copying from if. And actually, if you're going to, yeah. Go ahead. Yeah, from if part. Okay, I'll wait. So, and if you solve for x, what would you get if you solve for x? Anybody have any idea? Thank you. How about Emily? Let's say we wanted to solve for x. What would you do, by the way, to solve for x?
You would,
Let me give you a hint. Wouldn't you multiply both sides by AB? Or use the appropriate proportion? X times x equals 2?
that's what,
Wouldn't you get x times x? X squared is equal to?
80.
Yeah. And how would you solve for AB? X.
Square root.
Square root both sides, right? So actually you could actually solve for it this way. And since we're talking about positive numbers, right, for all x and y, x and a and b to be positive, do I need a negative square root of AB? Because whenever you square root both sides, you guys remember, we have to put?
The negative.
Yeah, plus or minus, right? Positive or negative. So, but we don't need the negative part because x is going to be positive. Again, we're going to talk about length of some segments and so forth. Okay, so even though algebraically you get x equals to positive or negative square root of AB, right? We don't worry about the one that's negative. Is that okay? So write that. I'll give you more time. Okay, so if you know this to be true, can you find the geometric mean between, thank you, 5 and 11? Go ahead, everybody try. So knowing this, how can you find the geometric mean between 5 and 11? Go ahead, everybody try. How about Krista? How would you find the geometric mean?
I'll discard it.
Uh-huh. Yeah, you just find the square root of 5 times 11, right? So that's just using that formula there. Or could I have used a over x equals x over b too? Would I get the same answer? Yeah. So there are two ways. You still get square root of 55. You could either set it up this way, set up the proportion, right? 5 over x equals x over 11. Right, and then of course you cross multiply or multiply both sides by the LCD. Or a property of proportion tells you that x squared is equal to 5 times 11. Square root both sides. And how come we don't have negative square root of 55?
Because x is positive.
Yeah, x is positive. We're talking about positive numbers. Okay, for geometry. Look, on the definition when we said a, b, x are positive. Well, yeah, geometry mean. Okay, and here, then we get, or you could use the equation x equals the square root of ab. That's easier. Right? But I'd like you to kind of know how to do this using the proportion, because that's going to be helpful for us as we talk about similarities in right triangle. Okay. By the way, if you have proportions, are every proportion set up this way? Would you get geometry mean for every proportion? No. But some of them will work this way, right? Some of them. Okay. And it's kind of nice because in a right triangle, this thing happens, this geometry mean. So we'll find out. Very good. All right, let's look at our first theorem then. Okay. So, theorem 8.1, sorry it doesn't have name. David, why don't you read this for us?
If the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other.
Okay, so what does it mean? Well, first of all, write this down and take a look at the picture. As you write it down and look at the picture, see if you can understand what this is saying. If the altitude is drawn from the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. Okay, so
Wait, what?
exactly. Go ahead and write it down. See if you can understand what it's talking about. We'll explain it in a minute. But try it yourself first. How about Reagan? What do you think this is saying? Yeah, all the triangles are similar. How many triangles do you see? 3. All 3 of these triangles, right? Okay, are similar. You know, one on the left, one on the right, and then the big one. Okay, that's what they're saying. But this doesn't happen every time, right? Obviously, you have to have a what kind of triangle to start with? A right triangle. And how are we going to draw this CN? That is the altitude that they're drawing, right? To the where? How about Nico? How are we drawing this hypotenuse? How are we drawing this altitude?
To the hypotenuse.
To the hypotenuse, I kind of said. So in order to draw an altitude to the hypotenuse, don't you have to start with that right angle and then go down to the hypotenuse? Okay, so once you do that, right? If you have any right triangle, once you draw an altitude to the hypotenuse, it forms 3 triangles, and all 3 triangles are similar. And so, how would you go about then proving this? That's the interesting part. So you're right. It turns out you just need angle. Go ahead, everybody. Well, how is it angle? Go ahead, everybody. Think about this. Why is this true? So why is it angle? Who can tell me? First of all, it says triangle ACB, the big one, is similar to triangle ANC. Let's look at those two first. Okay, the big triangle versus the one on the left. Okay, why these two similar? We said it's because of angle, right? Angle, similarity postulate. Why? Who could explain to us? How about Grace?
So the one, are we comparing the one?
Yeah, let me draw this one versus the big one.
Well, first the C and A
Mm-hmm.
is all 90.
Yeah, CNA is at 90 degrees, isn't it, guys? So that's 90, and also
And angle CAB, they share that?
yeah, they share both the big triangle and then the small. Don't they share this triangle? This angle A, and of course there's another right angle. So there's AA. Right? That's it. Angle. They're both right triangles, aren't they? And they share that angle A. So by angle, the two triangles are similar. We could do the same thing for the other one. Who could help me how to do the other one? How about this one? Yeah, and so, okay, we did this one right now, right, with the red. Okay, so we got these two. Now we're going to get this big triangle and this one, because if the big triangle and then the blue one are similar, guess what? By transitive property of similarity, the 3 triangles are
Similar.
yeah, they're all similar, right? So all I'm going to say is then the blue one and then the big one are similar. Who can help me how to do that? How about hold on, Julie? Okay, why are these 2 triangles, the one in blue and then the big one? Why?
Because they share an angle.
They share an angle right here. Yeah, angle B. Don't they both share that angle? And what kind of triangles are these? Both of them are right triangles. There's 90. There's 90. So by angle. Okay. So the ACB is similar to ANC, and ACB is similar to CNB. Therefore, by transitive, right? ANC is similar to CNB. They're all similar, right? Does that make sense? Yeah.
But is there like a postulate or a theorem that teaches 2 triangles are similar at the same time, but they're similar?
The property of similarity.
Does that make sense? You got it? Okay. So, there's that. Okay. Now, I want you to understand something. This is kind of important. You know, when you have a right triangle, there's one exception, but for every right triangle except 45, 45, 90, right? Could you have 45, 45, 90 triangle? Whereas an isosceles right triangle, you could think about it that. Except for that one, wouldn't one side be shorter than the other side in a right triangle? Unless it's 45, 45, 90, right? So notice how do you think naming these are important?
Yes.
In other words, do you think the corresponding sides must be corresponding, in other words? So look, take a look at this. Look at AC. Look at AC in this triangle. Let's say this is actually drawn to scale, okay? And let's say AC is the shortest side of this right triangle. Okay, look at the one on the right. Which one is the shortest side? On the right. AN. You see how if you go ACB, you gotta go ANC? Which side is shortest on the one on the right? CN. Does that make sense? Do you see how CN is the shortest side of that right triangle? So I want you to kind of understand that, because whenever you write these similarities, right, you got to do it with the corresponding vertices and so forth. If you don't, then it's not quite true. So from this, and we talked about geometric mean and so forth. How is that related? Well, take a look at this corollary. Hold on, let me move it up. Okay, somebody read this for us. How about Narek? Can you read this for us?
When the altitude is drawn to the hypotenuse of a right triangle, the length of the altitude is the geometric mean between the segments of the hypotenuse.
Okay, so it comes from the theorem. So as you can see, the first part is saying when the altitude is drawn from to the hypotenuse of the right triangle, just like what we had before. What are they saying? Then what? The length of the altitude is the geometric mean between the segments of the hypotenuse. Okay, so go ahead and write this down and think about what they're saying. Okay, go ahead, everybody. I'll wait. So, who could help us understand what this is saying? Madison, what do you think this means?
Well, like, since the triangle, like one triangle is proportionally smaller than the other one, and so it's saying like C and then C and T.
Okay, so we got this triangle, right triangle. We have drawn the altitude to the hypotenuse, right? Then they're saying the length of the altitude is the geometric mean. Which one of these is the length of the altitude? Cn. So can I just call that x? By the way, this is what we had from the previous, right? 3 triangles are similar. So can I go to right here, x? Is that okay? So if that's your x, what's your a? Because remember, if x is a geometric mean, remember we had this proportion, x, something over x equals to x over something, right? So what, and it was a and b, remember? What is your a in this case? They say, okay, the x is a geometric mean, then between segment of the hypotenuse, which segments are they talking about? So we have the hypotenuse AB. What are the segments of the hypotenuse? Yeah, a and AB. So which one is this? This is your, AN is your A. Guess what? MB is your B. Isn't that what we have here? AN, look, AN, A over X, CN, right? I don't know why they use these, but isn't it easier to use X, okay, X and AB. And then CN, again, is your X, and BN, that is the segment of the hypotenuse. This is always going to be true. Isn't that interesting? We just learned about geometric mean. This always happens. If you have a right triangle and you draw a hypotenuse to the, if you draw an altitude to the hypotenuse of this right triangle, this altitude of that right triangle is always going to be the geometric mean between the segment that this altitude separates. Isn't that nice? Okay. Why is this true though? So that's the important part. So okay, that's great, but why? How would you go about proving this? One person, 2, 3. Some of you. Okay, I'll give you some time. Think about it. I'll give you time. Why does this work? So many of you, I think, have an idea. Let's think about this together. Okay, so if this is what happens, a over x is equal to x over b, right? How could you prove this? Of course, this is a corollary. It actually uses that theorem previously. So who could help us? How about Brandon?
Wait, which?
Right. See?
So you do the previous theorem,
Uh-huh.
then you use the corresponding sides of similar triangles.
Exactly. You use the previous theorem saying, because it said all 3 triangles are similar. I even wrote it here. And we know that corresponding sides of similar triangles are in proportion. So mainly we're going to look at which 2 triangles?
A and C.
Yeah, the small one on the left and the little bit bigger one on the right. Right? Does that make sense? Yeah. So look at, guys, class, look at AN in terms of the one on the left. Isn't AN the shortest side of this right triangle? Look at CN. Isn't CN the shortest side of this? So look, AN the shorter side over Cn, which is, if I just look at the triangle on the left, it's not the hypotenuse. So there are two sides, right? There's the shorter side and then the longer side, right? Shorter side of the longer side equals to what? The one on the right? Which one is the shorter side in this case? The Cn, x, which happens to be the longer side of the one on the left. You know what I mean? That's why this x is a geometric mean, right? So you get Cn, which is the shorter side of the one on the right, over the longer side of the one on the right. Do you see how that works? Do you see how these are the corresponding sides of similar triangle? It's just that Cn and Cn, they happen to overlap. Right? Does that make sense? That's why Cn is the geometric mean. Yes? One on the left, Cn is the longer leg. One on the right, Cn is the shorter leg. Does that make sense? So shorter leg of the longer leg is equal to shorter leg of the longer leg of the one on the right. Do you see how that works?
Yeah.
Okay. So that's what we have here. Any question? Right? Look at the triangle. So it's easier this way. If you were to hide this triangle on the right, look, Cn is the, An is the shorter leg over the longer leg of this triangle on the left. Now, look. And we do the same thing. Shorter leg, now Cn is the shorter leg of the triangle on the right, and then MB is the longer leg. Right? And that's how we get this, right? That's X is the geometry mean there. Alright, let's move on to then the second corollary. Okay. Here we go. This one is very similar to the one before, but it's a little bit different. It looks kind of hard, but it's not really. Who would like to read this for us? How about Youngwoo? What do you think?
When the altitude is drawn to the hypotenuse of a right triangle,
Again, it's the same exact thing, right? All three of these starts the same way. Yeah?
each leg is the geometric mean between the hypotenuse and the segment of the hypotenuse that is adjacent to the leg.
Yeah. What does that mean? Is each leg? We know what each legs are, right? Each leg is each leg is the geometry means. We have two legs of this right triangle. Each leg is the geometric mean between the hypotenuse. Okay, we know what the hypotenuse of this big triangle is, right? Isn't that AB? And the segment of the hypotenuse that is adjacent to the leg. Okay, what does that mean? Okay, go ahead, write this down. See if you can figure it out. I'll wait. Actually, most of the times you just have to use it to find the actual length of these. So you know, most likely not. This is used mostly to figure out the length of these legs and so forth. Okay, so but write it down at least, and then figure out what this is talking about. Okay. So you're asking. Okay, so it turns out it's not that hard. Okay, so first of all, each leg is the geometry mean. There are two legs, right? In this, so whenever they're talking about each leg, they mean each leg of the original right triangle. And when they're talking about the hypotenuse, of course, hypotenuse is the original triangle. Okay, so let's write this down. First of all, what we have is we know that each leg is a geometry mean. So let's take one of the leg, AC. Let's call that x. Is that okay? Right? That x is the geometry mean. So it's going to be a over x equals to x over b. Right? Thank you. Correct? So there's my x. Right? And so which one of these is your x then? That's what we have to figure out. So we got the each leg. Geometry between hypotenuse. Which one? Where's the hypotenuse? AB. There's your A. That's your hypotenuse. Right? That's your A. And okay, and the segment of the hypotenuse, there are two segments, AN and MB, just like before. But which one do we want? That is adjacent to that leg. Which leg? The one that we just chose. X. Which one is the adjacent to the leg? AN. There is your B. You see what we have here? AB over, which is X, right? AC, which is, AB, which is A. AC is your X. And then X over, you see AN, that's your B. How many legs do we have in a right triangle? Two. Let's call this X now. If I call this X, right? So again, it's going to be A over X equals to what? X over B for this case, right? So if this is your X, it says what? Hypotenuse. Where's your hypotenuse? AB again. A over, where's the segment that is adjacent to that leg? And there you go. There's your B. Isn't that what we have? AB over BC, you see, is equal to BC over what? BN. There you go. That's what they're saying. Do you see that? Do you see what they're trying to say? And do you think, of course, to prove this, do you think we're going to use the same as before where two similar triangles are what? Corresponding sides of similar triangles are in proportion. That's going to work the same way for both of these.
So you just do it.
Yeah. Does that make sense? So that's how you, just like before, that's how you would prove. But do you see what they're trying to say though? Okay. Do you see what they mean by, look, each leg is the geometric mean, right? Between hypotenuse of the original right triangle, right? Hypotenuse and the segment of the hypotenuse that is what? Adjacent to this leg. There you go. Yeah, adjacent. So if you're talking about this AC, which segment is adjacent to this AC? Adjacent means next to it, right? Right here, AN. It can be MB, get it? Right, there are two segments of this hypotenuse. One should draw this altitude, right? Which one are they talking about? Well, the one that's adjacent to this leg, right? And if I chose the other leg, CB, which one is adjacent to this leg, CB? NB, right? Here it should be.
Why can't it be CN?
CN is not a segment of the hypotenuse, is it? Because when they say segment of the hypotenuse, they mean the original hypotenuse of that triangle ABC. Okay? Are we good? Okay, knowing these, okay, corollaries, now let's do some examples, okay? So here, why don't you all try this one? Use the diagram to find the value of H, A, and B. And do you think those two corollaries going to be helpful for us to find H, A, and B? I think so, very much so. Go ahead, everybody try. I'll wait for you. And of course, you could help each other out. Let's see whether we could actually use these corollaries, okay? Here we go. So to get H, I think a lot of you got H without any problem. Using the corollary, the first one.
Yeah.
Okay, we know that H is the geometry mean between 3 and 7. Isn't that what he said? So we just set it up like this, right? 3 over H equals H over 7. Well, H is equal to square root of 21. Easy?
Yeah.
Now, to get A, you use the corollary 2, actually A and B. To get A, first of all, look at the corollary. What does it say? Let's go back up. You see that AC is your geometric mean between the hypotenuse and the segment next to that leg, right? So we do the same thing for that. So what are we going to say for A? A is going to be the geometric mean of what? Class?
Over H equals H over 7.
Yeah, isn't this, look, A is a what? What is your hypotenuse? Isn't it 10 over A is equal to what? A over 3? And now you find A. So when you find A, don't you get square root of 30?
Yes.
Look at the second corollary. This is A is your geometric mean between the hypotenuse and the. No, that's what the theorem says. A, okay, is the geometric mean. So A goes down here and A goes up here, right? Between which two numbers? The hypotenuse of the original triangle and the adjacent. Yeah, the segment of the hypotenuse adjacent to this side A. Now to get B, we do the same thing. B is the geometric mean between what? 10 and 7. Because isn't 7 the segment of the hypotenuse that's adjacent to B?
Yeah.
So you set it up this way. BB 10 over B is equal to what? B over 7. What do you get as your answer? Square root of 70. Question? Good question. I was going to actually talk about this, guys. Listen, as you did in your algebra review from last night's homework, right? If I get square root of, I don't know, square root of 100, are you going to leave it as square root of 100? No. You're going to write? You're going to simplify this. If you get square root of 8, are you going to leave it as square root of 8? No. What if you get square root of 1 over square root of 2? Are you going to leave it this way? No. How are you going to simplify? Yeah, you may not have square roots on the denominator. Multiply top and bottom by square root of 2, square root of 2. What do you get? Rad 2 over 2. Do you see how you have to simplify this? That's why we gave you the algebra review. Do you understand how this works? These things work. Can you do this for your homework tonight? All right, good.